Hey, welcome back. I'm working up on this huge article on the shear stresses. Could you believe that stuff? Tau equals VQ over IT. That is some good stuff, good stuff, good stuff. Gotta get it in, gotta get it in, gotta get in. All right, we gotta work on a huge deadline. Oh my gosh, did you hear the shear stresses act in the longitudinal direction too? Wow, make sure I get that in there too. Oh yeah, I'll talk to you in a second. You gotta hold on. Oh my goodness, everything comes together at once. Gotta get the shear stress expose out. All right, print. Send that stuff to the printer. Let me grab it hot off the press. Here it is, best shear stress expose ever. Check it out. All right, yeah, what's that? Oh, I'm working up this huge story. Oh, it's all about shear stresses. Oh, well, let me duck into the phone booth. Yeah, it's this great expose on shear stresses. They're so important, you know. Yeah, I know. We saw them about beams. Yeah, I'm working the whole angle. I've got a print copy ready. It's already gone out. We're gonna put it to the presses. What's that? Something in the air outside? I don't think shear stresses are in the air. You think it's a bird? Is it a plane? Oh, it's Shearman! I'm here to rescue the day. I heard people were bored and falling asleep during the derivation, so I gotta wake you up. Let's go check out a demonstration. Let's look at a demonstration on how shear stresses work in a composite layered beam system. So if we take a look at this beam and I go ahead and I put a point load on it, so if I go ahead and I apply the point load, now I'm going to exaggerate the effect, so I'm going to just kind of keep displacing it, right? As we push down, we see that all the layers kind of resist that force. But you can see at the ends, we get some separation. So the layers of the system kind of separate in almost like a staircase manner. And so basically that happens because these layers are all individual pieces. So they don't have any means to pass that shear stress. You remember we said that when beams deflect, they have a shear stress in the longitudinal direction along the length of the beam. And if you have an unbonded system, then the individual layers don't really work together. And they can slide relative to one another, and that's why we see that movement at the side. Now, a more efficient system is to be able to pass the shear between the layers. So in most beams, if it's all one material, like we have a steel or a concrete beam, then the material itself is passing these shear stresses to each of the layers as we go down through the beam. But if you have a composite system of distinct layers, you need to somehow bond them together. So maybe you use some sort of epoxy or glue. Here I'm going to just bond them together by clipping the ends. So we're going to take these binder clips, just clip the ends. And what this is going to do is this is going to now force the layers to act as one unit. Alright, so now I have the layers. You can already see it's stronger. Before it was even just sagging under its own weight. Now you can see that it's stronger. And now if I go to put this point load on, now I have to push. I have to push a lot more, and I'm going to have to keep pushing quite a lot. And you can see my supports are sliding here. But you can see that the composite system is stronger than the previous system. And as it deflects or as it bends, the ends remain as one unit. So there's no kind of sliding action. So that's kind of what happens in a system and how shear stresses work. Let's go ahead and talk a little bit more about that and get this into your notes. Alright, so let's put this model into our notes. So I'm going to color the layers just like they were in the model. So the top layer is red. The middle layer was yellow and the bottom layer was blue. Excellent colors for Superman, if you ask me. Alright, so all we're looking to do is to capture the same thing that we saw in the demonstration, but make sure that when you go back to check your notes later, you'll actually remember this demonstration and indicate kind of the point of it. So again, when we had individual layers and we applied the point load to the middle, we saw that the individual layers kind of acted separate from one another. So the blue layer deflected and then the yellow layer on top of that deflected. But because they were not connected, we had sort of a separation at the ends, right? And it actually happens at the ends where the shear force is the max, and therefore the shear stress would also be the max there at the support. So go ahead and sketch these in, and then I'll color them in. Then highlight that staircase motion on the left-hand side. And again, we get that kind of action, that sliding between the layers, because it is non-composite, or the beam is non-composite, so the layers will separate. All right. In the second time we ran this little experiment, we saw that we used the binder clips to bind the edges of those foam sheets. So the 3 sheets acted as one unit. So we saw that the ends did not displace relative to one another. And in doing that, because it could handle that shear, the unit as a whole was stronger. So we're just going to sketch that in and get the colors in for the different layers. Then we'll be ready to talk about the system. So we recall back to the demonstration. Which cross-section was stronger? Well, the composite cross-section was stronger. Why was it stronger? What causes this sudden change in strength? Well, it's because that the shear forces between the layers are able to be passed from one layer to the next. And by doing that, the overall beam, all 3 layers together, will be stronger than when they were non-composite. Lastly, are there any consequences to this? So I want you to just take a couple seconds to think. Are there any consequences to binding the layers together so that shear forces are passed from one layer to the next? Well, of course there are consequences to this, and namely we just need to design for shear stresses in our segments. So if we're going to bind these layers together, whatever we're using to bind those layers, whether it be some sort of fastener, glue, maybe we use nails or bolts, or instead of glue, maybe epoxy if we're looking at like a carbon fiber layered system. And so we just have to design for the fact that these shear stresses exist. The other thing that could happen is that shear stresses can possibly cause non-uniform strains in the cross-section. So what does this mean? Well, if we have non-uniform strain, because shear stress has that longitudinal component, we could result in a violation of plane sections remaining plane and having some sort of warping happen. We said one of the problems with shear stresses is that they can lead to warping in the cross-section. So what is warping? Warping happens when plane sections no longer remain plane. When we have loads that are applied through the center of gravity of the cross-section, then the beam will bend downward and we'll have nice plane sections remain plane, and we keep all these, even though they're bent, it's still, the cross-section is still one plane. The problem is if the force, the shearing force is not through the center of gravity, or if you have an unsymmetric section. What that can lead to is non-uniform shear stresses causing movement in the longitudinal direction in your cross-section. So what does that look like? So say, for instance, we didn't have a load that was through the center of gravity, and it ended up creating like a torque on our I-beam. For the I-beam, you can see that as it torques, right, and I'll exaggerate it here, you can see the cross-section at the end there, it's not in one plane anymore. You can see that the top flange here has moved to the right, and this portion of the flange has moved to the left, and then at the bottom, the flange is opposite. And you can just see how it's kind of racked there, and it's no longer one plane in the cross-section at the end. So that's the problem that shear stresses can lead to. For the most applications that we're going to take a look at, we're going to be okay. We're not going to have any warping due to our shear applied to the system. But I just want to explain what warping is so you kind of have a visual idea of what it is for the future. All right, so the final thing to talk about is why is this even important, right? Well, of course it's important because shear failures can occur in our beams, and we have to be conscious. They're particularly dangerous in reinforced and pre-stressed concrete beams like that beam shown in the picture to the left. As you can see, the failure tends to be more explosive because we usually don't have much warning of failure, especially in a concrete beam. The shear cracks are very small. So we have little to no warning that something is about to happen until it actually fails. So we say it's a common problem in what are known as deep beams. Deep beams are beams that have a pretty large depth compared to their longitudinal length. And so you can see in the photo to the left where the reaction is on the left, bottom left, and where the load is applied up to the upper right. There's not a very far distance between those two, and that is where the shear failure will occur. For those of you materials or mechanical engineers out there that are going to use like carbon fiber layered systems or other kind of styrofoam and carbon fiber layered composite systems, shear failures are also something you definitely need to consider in terms of building the epoxy between those layers to make sure it won't fail. Finally, shear stresses are important because we noted that composite systems were stronger. So we do want to design for shear because we'll get a benefit from the system level. We'll get a benefit from that added stiffness if we have the different layers or the different portions of the cross-section being able to pass the shear stress back and forth. So hopefully I've convinced you that shear stresses are important in our beams. If you want to see a couple videos of failures, search concrete shear failures. Otherwise, in our next video, we're going to take on an example problem where we look at built-up cross-section.